On October the 9th, an X9 class solar flare erupted from the surface of the Sun. That is the strongest flare recorded in nearly a decade. 9 times the threshold of the most powerful category we track. The stakes are simple, and they are not small. A flare this size can degrade GPS accuracy, blackout high-frequency radio across entire hemispheres, and, if the geometry lines up, drive a geomagnetic storm strong enough to strain the power grid you are sitting under right now. In the next few minutes, we are going to walk through what actually happened inside that flare, what history tells us about storms like it, and the specific signs scientists are watching in the days ahead to know whether this becomes a footnote or a headline. Start with the number X0. Solar flares are ranked on a letter scale, A, B, C, M, X, each letter representing a 10-fold jump in energy output. X-class is the top tier, reserved for the flares capable of triggering radio blackouts on the sunlit side of Earth and radiation storms near the poles. The number after the letter is a multiplier. An X1 is already powerful. An X9 is 9 times that. For context, the flare that knocked out shortwave radio across parts of Asia and Australia in 2017 was rated X8.2. This one edged past it. Here is the single most important thing to understand before we go further. A flare and a geomagnetic storm are not the same event. The flare is light. It travels at the speed of light and reaches Earth in about 8 minutes, and its main effects, radio interference, some GPS degradation, are fast and usually short-lived. The storm is different. The storm is matter. It's a cloud of charged solar particles called a coronal mass ejection, and it travels far slower, taking 1 to 3 days to cross the 93 million miles between the Sun and us. The flash happened in an instant. The plasma cloud is still crossing space as you watch this. That is why space weather forecasters don't relax the moment the flare fades from the imagery. They shift immediately to a different question. Was there a coronal mass ejection embedded in that eruption, and is Earth in its path? Answering that requires coronagraph imagery, cameras that block out the Sun's blinding disk to see the faint structure of plasma blooming outward around it. If a bright, expanding halo shows up centered on the Sun, that's the signature of a cloud heading roughly toward us. If the ejection is angled off to the side, Earth gets a glancing pass instead of a direct hit, and the story quietly de-escalates. Now, bring that back to your own house for a second. Space weather has a direct line into the systems your town runs on. Geomagnetic disturbances induce electrical currents in long conductors, and a power grid is essentially one enormous conductor strung across a continent. Enough induced current in the wrong transformer at the wrong voltage, and you get equipment damage, not just a flicker. GPS timing signals, the ones banks and cell towers and air traffic control quietly depend on down to the microsecond, can drift. Airlines reroute polar flights during severe storms specifically because HF radio, the backup communication system for planes flying near the poles, can go dead for hours. Consider the case that every space weather scientist still measures everything else against the Carrington Event of September 1859. A pair of solar flares triggered a geomagnetic storm so intense that telegraph operators across North America and Europe watched their equipment spark and, in some documented cases, keep transmitting messages after they disconnected the batteries, running purely on induced current from the storm itself. Auroras were visible as far south as the Caribbean. Gold miners in the Rocky Mountains reportedly woke up and started making breakfast, convinced dawn had come, because the sky was glowing that brightly at 1 in the morning. That was a world with exactly one electrified technology worth damaging: the telegraph. A Carrington-scale storm hitting a modern, grid-dependent, satellite-reliant civilization is a scenario space agencies actively wargame because the estimated economic cost runs into the hundreds of billions concentrated in the first few days. Here's the self-correction though, and it matters. This flare is not a Carrington-level event, And treating every X-class flare as an extinction-level countdown is exactly the kind of overhype that erodes trust in real warnings when they matter. The Carrington storm is estimated to have been driven by an unusually fast, unusually dense ejection, slamming into a magnetic field already primed to receive it. Most X-class flares, even ones this large, don't produce a storm anywhere near that severe, because the ejection's internal magnetic orientation has to line up just right with Earth's own field to unlock the worst effects. Get that orientation wrong, and even a strong storm mostly produces beautiful aurora and very little damage. The size of the flare tells you the potential energy involved. It does not by itself tell you the outcome, and that brings us to the part where people usually reach for the wrong explanation. Every time a major flare makes headlines, some corner of the internet frames it as evidence of something being deliberately hidden, a government cover-up of an incoming solar kill shot, or a claim that agencies are suppressing the true severity to prevent panic. That's not what's happening, and it's worth saying plainly why. Space weather data is some of the most transparently published scientific information that exists. Coronagraph imagery from spacecraft is posted publicly, often within hours. Geomagnetic storm forecasts are issued on a public scale, updated multiple times a day, free for anyone to check. The reason forecasters sound cautious isn't concealment, it's that the physics genuinely doesn't allow precise prediction this far out. Nobody, anywhere, can tell you 3 days in advance exactly how strong a storm will be when it arrives, because the details depend on measurements taken by a single spacecraft parked about 1 million miles from Earth, and that data only becomes available roughly 15 to 60 minutes before impact. That's not secrecy. That's the actual limit of the science. So where does that leave us with this particular flare? The mechanism is the thing to hold on to here. Flares like this originate from sunspot regions, patches on the sun's surface, where the magnetic field has become so tangled and compressed that it eventually snaps, releasing energy that had been building for days or weeks. Think of it less like a random explosion and more like a rubber band being twisted past its limit. The region responsible for this flare has been active and growing for several rotations of the sun, and active regions like that don't typically produce just one major flare and go quiet. They tend to keep firing as the twisted magnetic field works through its stored energy, which is exactly why forecasters are treating the days immediately following this event as a heightened watch window, not a closed case. That is the mechanism. Here is what to actually watch for as this plays out. Number 1. Coronagraph confirmation of a coronal mass ejection and its direction. This is the single fact that determines whether the story escalates or fades. A clear, halo-shaped ejection centered on the sun means a plasma cloud is very likely inbound. A narrow jet off to one side means Earth mostly gets spared. Number 2. The arrival and measurement of the ejection's internal magnetic field once it reaches the solar wind monitoring spacecraft stationed upstream of Earth. This happens only in the final hour or so before potential impact, and it's the detail that decides whether a storm is a minor disturbance or a severe one. If that field points opposite to Earth's own magnetic field, the two connect efficiently, and energy pours into our magnetosphere. If it points the same direction, much of that energy simply glances off. Number 3. The planetary geomagnetic index, tracked on a scale from 0 to 9, which measures how disturbed Earth's magnetic field actually becomes in real time. Numbers in the 5s start to matter for high-latitude power grids and aviation routing. Numbers in the 8s and 9s are the range where the Carrington-level comparisons start to become genuinely relevant rather than just clickbait. Number 4. Whether the active sunspot region rotates further into direct alignment with Earth over the coming days or begins to rotate away toward the sun's far side. An active region pointed straight at us is a loaded gun. The same region, a week later, rotated toward the limb of the sun, is mostly just something we watch from a safe angle. Number 5. Aurora visibility reports at unusually low latitudes. This one is for you, directly. If people in regions that almost never see the northern or southern lights start reporting them, That is a real-time, visible confirmation that a significant geomagnetic storm is actually underway. Not a forecast anymore, but an observed fact playing out over your own sky. Connect all 5 of those back to the flare we opened with, and you have the actual chain of cause and effect. Energy builds in a twisted magnetic region, releases as a flare, potentially launches a cloud of charged plasma. And that cloud's speed, density, and magnetic orientation, measured only in the final hour before arrival, determine whether the next few days bring a quiet, astronomical curiosity or a genuine strain on the infrastructure modern life depends on. Here is the single most important thing to carry forward from all of this. We are, as a civilization, more exposed to space weather today than at any point in human history. Not because the sun has gotten more active, but because we've built more things that depend on the stability of Earth's magnetic environment. Satellite, precision timing, transcontinental power grids, polar aviation routes. None of that existed in 1859. All of it exists now, layered on top of each other, largely invisible until something disturbs it. That is the quiet dread underneath a story like this one. Not that the sun is unusually dangerous right now, but that our tolerance for disruption has quietly gotten thinner every decade, even as the underlying physics hasn't changed at all. The reassuring half of that same fact is that we now watch the sun more closely than we ever have. Multiple spacecraft image it continuously. Forecasting centers around the world share data in real time, and the lead times on the biggest warnings, while imperfect, have improved substantially in just the last 20 years. This isn't a story about helplessness. It's a story about a genuinely powerful natural system that we are learning, slowly and imperfectly, to see coming. So here's where this leaves you, practically. Nothing about an X9 flare demands that you do anything differently today. Power grids have hardening procedures. Satellite operators have contingency modes. This isn't a call to panic. It's a call to pay attention. Because the difference between a storm that makes the news for a night and one that actually disrupts your week comes down to those specific numbers we just laid out: the direction of the ejection, the orientation of its magnetic field, and how high that geomagnetic index climbs once it arrives. Watch the coronagraphs, watch the geomagnetic index. Those 2 data points, more than any headline, will tell you how this actually ends. If you want to understand these systems before they become the story, the ones building underneath the ocean, underneath the ice, underneath the ground you stand on, and now, apparently, 93 million miles over your head, that's exactly what this channel exists to track. Subscribe if you want the next one explained the same way, clearly, and without the hype. Share this with someone who still thinks a solar flare is just a pretty light in the sky. And if you have questions about what we covered, leave them below. We read every one. The sun isn't finished with this active region yet. Neither are we.